Black holes are points in space that are so dense they create deep gravity sinks. Beyond a certain region, not even light can escape the powerful tug of a black hole's gravity. And anything that ventures too close, be it star, planet, or spacecraft, will be stretched and compressed like putty in a theoretical process aptly known as spaghettification. A black hole is a region of spacetime where gravity is so strong that nothing, no particles or even electromagnetic radiation such as light, can escape from it. The theory of general relativity predicts that a sufficiently compact mass can deform spacetime to form a black hole. The boundary of no escape is called the event horizon, although it has an enormous effect on the fate and circumstances of an object crossing it. According to general relativity, it has no locally detectable features. In many ways, a black hole acts like an ideal black body, as it reflects no light. Moreover, quantum field theory in curved spacetime predicts that event horizons emit Hawking radiation, with the same spectrum as a black body of a temperature inversely proportional to its mass. This temperature is on the order of billionths of a Kelvin for black holes of stellar mass, making it essentially impossible to observe directly. There are 4 types of black holes: stellar, intermediate, supermassive, and miniature. The most commonly known way a black hole forms is by stellar death. As stars reach the ends of their lives, most will inflate, lose mass, and then cool to form white dwarfs. But the largest of these fiery bodies, those at least 10 to 20 times as massive as our own Sun, are destined to become either super-dense neutron stars or so-called stellar mass black holes. In their final stages, enormous stars go out with a bang in massive explosions known as supernovae. Such a burst flings star matter out into space but leaves behind the stellar core. While the star was alive, nuclear fusion created a constant outward push. Black holes of stellar mass form when very massive stars collapse at the end of their life cycle. After a black hole has formed, it can continue to grow by absorbing mass from its surroundings. By absorbing other stars and merging with other black holes, supermassive black holes of millions of solar masses may form. There is consensus that supermassive black holes exist in the centers of most galaxies. The presence of a black hole can be inferred through its interaction with other matter and with electromagnetic radiation such as visible light. Matter that falls onto a black hole can form an external accretion disk heated by friction, forming quasars, some of the brightest objects in the universe. Stars passing too close to a supermassive black hole can be shred into streamers that shine very brightly before being swallowed. If there are other stars orbiting a black hole, their orbits can be used to determine the black hole's mass and location. Such observations can be used to exclude possible alternatives such as neutron stars. In this way, astronomers have identified numerous stellar black hole candidates in binary systems, and established that the radio source known as Sagittarius A, at the core of the Milky Way galaxy, contains a supermassive black hole of about 4.3 million solar masses. As of 2021, the nearest known body thought to be a black hole is around 1500 light-years away. Though only a couple dozen black holes have been found so far in the Milky Way, there are thought to be hundreds of millions, most of which are solitary and do not cause emission of radiation, so would only be detectable by gravitational lensing. The no-hair theorem postulates that, once black hole achieves a stable condition after formation, a black hole has only 3 independent physical properties: mass, electric charge, and angular momentum. The black hole is otherwise featureless. If the conjecture is true, any 2 black holes that share the same values for these properties or parameters, are indistinguishable from one another. The degree to which the conjecture is true for real black holes under the laws of modern physics is currently an unsolved problem. These properties are special because they are visible from outside the black hole. For example, a charged black hole repels other like charges just like any other charged object. Similarly, the total mass inside a sphere containing a black hole can be found by using the gravitational analog of Gauss's law, far away from the black hole. When an object falls into a black hole, any information about the shape of the object or distribution of charge on it is evenly distributed along the horizon of the black hole, and is lost to outside observers. You can't directly see a black hole. Because a black hole is indeed black, no light can escape from it, it's impossible for us to sense the hole directly through our instruments. No matter what kind of electromagnetic radiation you use, light, X-rays, whatever. The key is to look at the hole's effects on the nearby environment, points out NASA. Say a star happens to get too close to the black hole, for example. The black hole naturally pulls on the star and rips it to shreds. When the matter from the star begins to bleed toward the black hole, it gets faster, gets hotter and glows brightly in X-rays. The first black hole wasn't discovered until X-ray astronomy was used. Cygnus X1 was first found during balloon flights in the 1960s. But wasn't identified as a black hole for about another decade. According to NASA, the black hole is 10 times more massive to the Sun. Nearby is a blue supergiant star that is about 20 times more massive than the Sun, which is bleeding due to the black hole and creating X-ray emissions. Black holes are only dangerous if you get too close. Like creatures behind a cage. It's okay to observe a black hole if you stay away from its event horizon. Think of it like the gravitational field of a planet. This zone is the point of no return. When you're too close for any hope of rescue. But you can safely observe the black hole from outside of this arena. By extension, this means it's likely impossible for a black hole to swallow up everything in the universe.